Hello everyone and welcome to PyCall Chain Rules Lightning Talk at JuliaCon 2022. We all know Julia has a cricket interop story. I've been using Julia since version 0.3 or something, having PyCall, RCall, etc. as escape hatches with minimal friction to use has always made it a very productive language even when it had a much smaller ecosystem. In machine learning and other related fields, Python happens to still be the de facto standard, with most new exciting research work being released in Python. While a lot of it is of course bindings around native code, building Julia bindings for the same native code is a much bigger effort, and often does not give a straightforward way to interact with existing Python user code. So this library grew from a need to be able to call existing PyTorch or JAX implementations and using it with Julia's exceptional gradient optimization tooling without re-implementing all of it again in Julia. This is fairly useful, especially for GPU code, where Julia often doesn't have all the same kernels implemented, and writing your own GPU kernels, while much nicer in Julia, is still a much bigger effort. And in some ways, all the ingredients already existed in the ecosystem for this library to exist. We already have PyCall, which allows seamlessly calling Python code from Julia while providing no copy conversion of NumPy arrays to Julia arrays. The only unfortunate thing about NumPy is that CPU only, and in Python land, all popular autodiff frameworks re-implement their own array interface as well as their own accelerator support. So NumPy by itself, like just using PyCall, is not going to be enough. So that's where DLPack came to our rescue. Like Python people also understand they have a lot of proliferation of these array interfaces, and therefore they have kind of settled on DLPack as the stable in-memory data structure for their arrays and tensors. So all libraries kind of support importing and exporting these DLPack tensors. And due to its clean C API, it's also very easy to access these DLPack arrays or tensors from any other language, like Julia. So Pablo Zubieta did all the hard work of writing DLPack.jl, which provides a Julia interface to this protocol, allowing zero copy sharing of both CPU as well as CUDA arrays from Python, while taking care of like small things like converting from column major to row major and like how to use those correctly. Finally, on Julia's side, things have largely converged on using chain rules for defining gradient rules for their package functions, which then can be integrated by the various Autodesk frameworks like Zygote, Jota, Diffractor, etc. This is exceptionally nice because then what we need for our library is just to define a custom Python function wrapper and the corresponding, say, reverse mode gradient rule, while appropriately using a DLPack behind the scenes for array transfer across Julia and Python. And once we have all that, it should just magically just work with everything that we have in Julia. So how does like basic things look like? So for an example using PyTorch, as you can see, we can just easily access any torch material that we want to use it. If in this case, like a simple dense layer, which is called linear in PyTorch, we just wrap it inside a torch material wrapper, and that's it. As a user, you don't actually have to think about it anymore. Uh, It's just a standard Julia function for you now, which would automatically work with all the differentiability toolings that we have in Julia. So, for example, if you wanted to compute the gradients for this particular a module with a particular loss function objective, this is all you need to do. And again, as you'll notice, this is, if you are familiar with the standard approach in Julia, this is literally, there is no difference at all. The JL wrap thing is now just a standard Julia function, which behind the scenes is obviously doing all the stuff that is required. I think a lot of people are interested in at least knowing the performance, although I don't necessarily see the performance being the most optimal is necessarily that hard a requirement, because even it would still be useful if you could just test things with Python and then decide whether it's worth re-implementing everything in Julia. So for different batch sizes, for forward mode and backward mode, we see about 2 to 3 times of an overhead for like basically the gradient computation as well as the forward mode computation, which is not too bad, but although I have not even tried optimizing this as much. But on the CUDA side, it's again it's maybe somewhat larger, especially with larger batch sizes. The backward pass can be more than sometimes 5 times more expensive. But overall, it is like in the same ballpark. Although I would clarify there are still some bugs remaining in the DLPack interface. So now I'll demonstrate some simple examples on how this allows us to integrate any of our Python models or network or layers into the Julia ML ecosystem. For example, if you had a torch module, in this case a sequential, which is equivalent to flux chain, and a bunch of linear layers, you could integrate it into the flux chain as a torch module wrapper around your torch module. And that's it. Now it's like a Flux model, and you can easily use the same tooling that Flux now suggests to use optimizers, setting up the optimizers, computing the gradient using the flux.gradient function or the particular loss function that you might have defined, and just updating the state of the system, state of the optimizer state, basically. So this, again, no difference at all. Similarly, if you want to take a Jack example, a similar effort on the Julia side is what's called the Lux.jl, which works with explicit parameters and everything else. Again, you can just build a similar Jack's models tend to have like an initialization function and apply function. You can wrap those inside a Lux wrapper, and then again use it in a Lux chain with the Lux tens modules, and you just do the setup as you would do for a Lux model. Then you run the optimizer loop, compute gradients with Zygote, update your optimizer parameters, and that's it. Again, extremely simple from a user perspective. All the complications are being handled behind the scenes. So to summarize, I talked about PyCall chain rules, which provides a simple interface to interact with existing differentiable Python code. And the GPU and CPU tensor interop is handled behind the scenes via DLPack. And this has exceptional productivity benefits from the perspective of just if evaluating and testing whether some code is worth translating to Julia, as well as like at least allowing at a short gap to uh, make certain changes that allow you to at least execute the full pipeline and then slowly move parts of your Python to Julia. And this largely builds on existing libraries and kind of demonstrates Julia language exceptional compositionality. The library is, of course, far from complete. There are still some GPU memory leak issues to resolve with DLPack, especially with the interaction between Julia, CUDA.jl, Python, and PyTorch garbage collectors. We still need to complete. I'm still working on completing the Python call chain rules, which is alternative to PyCall. And we can now both JAX and PyTorch also have forward mode AD, which can again be hooked up with the forward mode tooling in chain rules, which is frule. But again, not a lot of like forward mode libraries exist that easily use frule, so it's not been a priority. And of course, we need more examples and documentation. So yeah, that's it. Thanks for your time.